When I thought about what would be some appropriate talks for this conference that's looking back quite a ways, I remembered seeing a wonderful presentation by Bonnie Ellis here of taking a really long look back at Flathead Lake and bringing it up to the present, looking at long-term studies both of nutrients as well as trophic interactions in the lake, and I thought that would be really interesting. And Bonnie Ellis got her PhD here at the University of Montana. She's now a research professor in the Division of Biological Sciences and up at the biostation there at Flathead Lake. And I don't want to take any more of her time because she's got, I'm sure, some beautiful slides and some interesting slides. And just to warn the other speakers, I've got a little 5-minute and 1-minute signs to hold up, and 5 minutes means 5 more minutes for your talk, and I'm saving a little time for questions after that. So.
Thanks, Vicki. Glad to be here. I kind of wonder when we're going to see Flathead Lake like this again. We used to play ice hockey out there and ride our mountain bikes, and it hasn't frozen over since the 80s, but it froze over 3 times during the 80s. But it's been a long time. Flathead Lake is the 79th largest lake in the world. It's fairly deep, 116 meters deep. It has a large catchment, 18,000 square kilometers in size about. A large percentage of the catchment is in wilderness and managed forest lands, about 61%. And it has a very fast residence time. That is, if you were to drain the lake and put a plug in at the other end and let the tributaries fill it back in again in precipitation, it would only take about 2.2 years on average. Early on in our monitoring program, we began to see changes in water quality in Flathead Lake. And this graph shows our long-term trend in primary productivity in the lake. That's a measure of the ability of the lake to produce algae. So the higher that number is, the poorer the water quality. We also began to see declines in oxygen in the bottom waters of the lake, and we began to see algal blooms of noxious blue-greens that actually contain toxins. This particular bloom is of Anabaena flossaquia, and it occurs with another green algae, Botryococcus brownii, and we're beginning to see that algae, this is Botryococcus, even in the springtime. This is right along the east shore, not too far from the biological station. So we're really starting to see a lot of lake-wide blooms, and we have a very good history of not only phytoplankton but zooplankton and even fisheries in Flathead Lake, because the biological station is the oldest active biological station in the United States. It was established in 1899, and so there have been limnologists working on Flathead Lake periodically since the late 1800s. And this is probably the metric that we hear most about from old-timers around the lake. I started to say people who have lived there 60, 70 years, but I'm not going to call a 60-year-old an old-timer anymore. So we haven't been monitoring periphyton except for the last 10 years, but we did have a student that worked on periphyton in 1987, and this is the mean chlorophyll concentration of the algae that's growing on rock surfaces. And you can see that the number was quite low in 1987 in comparison to the last decade. And there's a lot of interannual variation here, but each one of these numbers, this is a mean of 10 different scrapings of the algae off of those rocks. Each one of these is significantly different from this value. And notice 2008, it's 10 times the concentration that we were seeing in 1987. So those old timers are really right in that they said, when I used to swim in Flathead Lake, the rocks were clean, I never used to slip on them, and now they're all slimy and slippery. And this is something we've only monitored here recently. And we learned from some early experiments we did on Flathead Lake that algae in Flathead Lake are stimulated by both nutrients, nitrogen and phosphorus. Initially, we thought phosphorus was probably the nutrient that would stimulate algae more because of the nitrogen to phosphorus ratio, but it's rather close to this theoretical ratio where either could stimulate the production of algae. This is sort of an old slide, but basically this line shows the response of the community to the addition of both nitrogen and phosphorus, whereas this is the result of controls with no added nutrients and controls with just nitrogen or just phosphorus. So at different times of the year, both nutrients can stimulate the production of algae. But this actually needs to be repeated. It was done in the late 90s, and things have actually changed quite a bit. Now, where are the nutrients coming from? This is probably the easiest source to get at, and that's a point source coming from our sewage treatment plants. And early on in our work, the Department of Environmental Quality noticed that there were several signs of declining water quality, and knowing the N to P ratio for the lake, figured that it would be a good idea to enact a phosphorus reduction strategy. And so they required that all the sewage treatment plants in the basin upgrade for additional removal of phosphorus, and they also placed a ban on the sale of phosphorus-containing detergents. And this was really quite successful, not just for Flathead Lake, but probably also for a lot of the smaller lakes that have septic systems around them because of the ban on phosphorus-containing detergents. So what you see up here is the metric tons of phosphorus per year coming from the various sewage treatment plants in the basin. And you can see the dramatic reduction in phosphorus that occurred when they upgraded the sewage treatment plant. Unfortunately, nitrogen is increasing. So the change in the way the plant was operated actually led to an increase in nitrate, at least from the Kalispell sewage treatment plant. And we don't have early data on ammonium, but you can see quite a lot of ammonium coming from the Whitefish treatment plant. So a lot of nitrogen still to worry about. And remember, both nutrients stimulate the production of algae. And then non-point source pollution, a little bit harder to get at those diffuse sources. But late in the 90s, we decided to do some synoptics where we go out and in one day with several crews measure discharge and nutrients all along the corridor of various rivers in the basin. We did the Stillwater, the Whitefish, the Swan, Stoner Creek, for example. And then we also looked at land use activity, land use cover as you move down those rivers. So as you can see in these histograms, as you go from headwaters to the mouth of the Stillwater River, you can see that land use changes from primarily forestry to a bit more clear cuts in this region, some forest management, to more agricultural uses. Grasslands is probably primarily grazing, but there's some ranchettes in here and urban development. And as you see that change in land use activity, you see along that same trajectory a change in the nutrients coming in. So land use activities without sufficient buffer strips between those activities and your water bodies can lead to increased transport of nutrients to those water bodies. Another source of nutrients that a lot of people forget about is the airshed. And some of this we can control locally in our region, and some we can't. It can be very global. So when they decide to burn the sod fields in Spokane, if the prevailing winds are in our direction, we're going to get the nitrogen and phosphorus coming from that burning activity. And with increased drying climate in this region, we might see more wildfires and hence more nutrients from wildfires. So anywhere from 15 to 40% of the nitrogen and phosphorus budget can come from aerosol deposition, not only the gases in the atmosphere, but also the particles that are falling on the lake surface. And this is just a day in Yellow Bay when there were actually no clouds in the sky. This is all from smoke. We get a lot of air inversions in the Flathead Valley, just as you do in Missoula. And this can really trap a lot of regional sources, and it can even trap smoke that's coming from elsewhere. It just sort of settles into the basin and then deposits on everything. And for those of us working on aerosol deposition, you can see it with your own eyes just in wiping off your picnic table before you sit down after one of these events, or filtering a sample of precipitation after one of these big events. And what I wanted to point out here was how high ammonium is. You do get phosphorus from these sorts of aerosol events, but usually only close to where the fire is occurring from the actual particles. So phosphorus is at least often quite low during this period, but nitrogen in particular can be quite high. So when looking at our long-term database going back to 1977, where we have continuous data, we see significant increases in ammonium and nitrate from aerosol sources and significant increase in nitrate from the Flathead River. There has also been an increase in nitrate at the middle of Flathead Lake and at the outlet. So you have more nitrate coming downstream from Flathead Lake as well. So we really thought the story was mostly about nutrients stimulating the production of algae. But we also knew that there had been food web changes in Flathead Lake, and that had the potential to affect algae and the cycling of nutrients as well. So we began to look closer at the food web in Flathead Lake. And there's a long history, a very long history, of food web manipulations in Flathead Lake. The U.S. Fish Commission began shipping fish to Montana in 1903. And I think it was by 1924 there were 12 fish hatcheries in the state. And over 19 different species of fish have been introduced to Flathead Lake. And what you see here are those that became abundant. So the species diversity in Flathead Lake was basically doubled by this addition of fishes over the years. And these are the dates these fish were introduced. The ones in red really became abundant, and the one in orange was very abundant for a few months or a few decades, and I'll tell you a little bit more about that. And I'm sorry for those of you who live here locally, you probably know this next short story, but I think you'll learn something new that we just learned in the last few years. After all of these fish introductions, which actually continued into the early or late 60s, the Department of Fish, Wildlife, and Parks introduced this shrimp. It's called Mysis relicta. It's a little opossum shrimp. It's about a half an inch or a little bit bigger, 3/4 of an inch in size. And they introduced it as a potential food for the sport fish to try to increase the size of the fish that sportsmen were so interested in. And this is the favorite food of mysis. It's a zooplankton, a really large zooplankton, but kind of slow compared to the other zooplankton. So he's pretty easy to get a hold of and eat. So this is the favorite food. It's called Daphnia thorata. But unfortunately, this was also the favorite food of the kokanee salmon. Now, the kokanee were not native to Flathead Lake, but they were quite beloved by everyone who lived there because they were easy to catch and they were delicious, and people even came from out of state to can them and freeze them and take them home on huge loads on their trailers. So this species is a site-specific feeder, and it's in the pelagic, the upper waters of the lake, whereas mysis sits on the bottom of the lake during the day and comes up at night to feed, thereby avoiding predation by the fish. So at this time in our work, we thought that the decline in kokanee that you see here, the kokanee colored histograms, that this decline was due to mysis really increasing and outcompeting them for their food resource, because they both liked the same food, but mysis could avoid predation by the fish and outcompete them for that food resource. But we've learned a little bit more. It was certainly part of the picture, but something else happened as well. And you can note the decline here. And this graph shows this dramatic trophic cascade that happened throughout the food web and affected eagles that were migrating to Glacier National Park to feed on the kokanee salmon that were spawning in McDonald Creek. So as the kokanee were doing well and going up into McDonald Creek, the eagles would fly from elsewhere, and they got up to around 600 at any one time. You could see 600 bald eagles along McDonald Creek. So when the kokanee crashed, the eagles went elsewhere. So the addition of this one little shrimp upstream of Flathead Lake and other lakes upstream found its way to Flathead Lake, took off. Oops, what did that do? I accidentally hit the wrong. Yeah, interesting. So caused this amazing trophic cascade that extended all the way to bald eagles at the top of the food chain and all the way down to zooplankton that we knew about at that time, which was the food resource for both of these critters. So then we had a look as we were wondering what other fishes were affected by this trophic cascade, we looked a little closer at the fish data that we had from Fish, Wildlife, and Parks and the tribes, who have been conducting very standardized gill netting since the early 80s, 1981, 1983, and then from 1995 on. And these pie diagrams show the abundance, the relative abundance of the various fishes in these gill nets. And on the left are the pre-mysis fishes in floating and sinking gill nets. These are shoreline gill net sets. And these are the fishes post-mysis in floating and sinking gill net sets. And what we see is that in the floating gill net sets, primarily native species before and after mysis, but the proportion of the abundant species really changed. We see a big decline in cutthroat trout, the gray here, a decline, significant decline in bull trout in the red, and northern pike minnow did quite well. So still native species, but a reduction, big reduction in these two species. In the sinking gill nets, quite a different story. We go from primarily native species to primarily non-native species. Lake trout increased by 19 times. Lake whitefish increased by 5 times at the expense of peamouth. And what is not shown here very well is the abundance of kokanee. Kokanee were actually very, very abundant, but they're pelagic. And these are gill nets that are set in the shoreline areas of the lake. So we have other estimates of kokanee, and they were very, very abundant. After mysis, completely eradicated. This just summarizes the previous slide, natives pre and post mysis, but the composition changed. And a 3-fold reduction in natives and a 4-fold increase in exotic fishes following mysis. So we were able to add to this, the previous graph that I showed you. I removed the eagles from that graph because they've gone away. And so you can see where we had the decline in kokanee, this big increase in mysis. But notice how this really dropped off at the same time lake trout took off. So lake trout were introduced 80 years prior to mysis, and yet they remained in very, very low numbers until mysis appeared. And this is because finally there was food on the bottom of the lake for young lake trout. The lake trout that were in the lake all the time, there just wasn't much food for the young of the year on the bottom of the lake. So once mysis showed up on the bottom of the lake, they could really take off. And once they get big, they're predatory on other fishes. And when they're up to 60 centimeters in size, they're eating almost entirely mysis. So these guys really are primarily responsible for this big decline you see in mysis, along with lake whitefish. Lake whitefish are also eating quite a lot of mysis, but lake trout are a real big player here. So notice the bull trout, a decline in the bull trout. They remain fairly low now, but seem to be hanging on. There's a lot of fluctuation, some pretty big peaks in lake trout here. So when they're bigger than 60 centimeters, they're eating a lot of fish. They're eating native fishes. They're even eating their own. They're very cannibalistic. So very, very big top predator. So this was the top predator in Flathead Lake before mysis. This is bull trout, threatened species, particularly in Flathead Lake. And this is the top predator now, which is actually quite beloved by our local fishermen. I think it's like pulling in a big old boot, but so this trophic cascade extended well beyond the fishes. This is what happened to the zooplankton. This is the zooplankton abundance in various groups of zooplankton prior to mysis, and this is the abundance in these various groups post-mysis. So you can see zooplankton took a really big hit right after mysis. Half the population was decimated, and it's beginning to come back. But what was really hit hard were the really big ones, the cladocerans. They were reduced by about 84%. But every single group took a pretty big hit, and there's a lot of recovery going on. But major species shifted. The species that dominated each of these groups shifted after mysis. There are some species that have completely disappeared from the lake, and there's some new ones on the scene. And this is just to show you some of the species composition of a few of the critters. These are some rotifers. You can see they were very abundant, some of them weren't, and now they are. This was the most dominant copepod before mysis, and you can see a little bit of recovery here, but not much. And so the size distribution of zooplankton has changed. We have a lot more small zooplankton out there and a lot less big zooplankton. And so if you have different fish, they're eating different size zooplankton. And if you get different size zooplankton, they're eating different sized algae. So yes, the trophic cascade did extend all the way to the phytoplankton. This graph shows the ability of the lake to produce algae. The small gray dots are those numbers. And this black line shows the trend in primary production before, during, and after mysis. We did a Bayesian analysis of this data and showed that there was a step increase in primary production that occurred because of this cascade, because of the change in the zooplankton population. So what I want you to take from all of this is that it is very complicated trying to understand what controls the phytoplankton production in Flathead Lake. Not only do nutrients influence the production of algae, but food web influences algae as well. So a very detailed food web model is needed, and that's what we're working on. We have a food web model that goes up through the zooplankton, but we need to bring fish into that picture as well. So we're trying to find some funding to complete that, because to really understand where you need to make changes to improve water quality, you have to understand predators as well as nutrients affecting primary production. And Vicki asked me to talk to to you about a few of the threats that I envision for Flathead Lake. And of course, one is continued invasives, either illegally or intentionally or accidentally. These are some of the fish that have made it into the Flathead now, or in the Flathead region. And I have to say my dentist just harasses me. Every time I go, I'm going to have to change dentists about putting walleye in Flathead Lake. How wonderful they are to eat and how beautiful they are. But so I know they're on the horizon. I took my class to Lake 5 last year, and we caught a really large walleye. So there's a lot of illegal introductions. Fishermen love to bring the fish they fish somewhere else with them and put them and try them out in Flathead. But I consider this to be probably the single greatest threat to Flathead Lake, and that's the appearance of this mussel, either the quagga or the zebra mussel. And it found its way to the United States in ballast water from ships coming over from Europe, and didn't show up until the late 80s, and it has already made it across to the western United States, and it's coming on trailers and boats because these things can be as small as a grain of sand, and adults can live in air. I forgot now, for several days, I think. Larvae can stay alive in water for several weeks or a couple of weeks. So it's really easy to transport them on a boat if someone's not completely disinfecting their boat as they go from one water body to another. So that's how we suspect a lot of these and know some of the introductions and how they occurred. So we're really worried about this critter because the impacts are just phenomenal, and they've already been described for a number of the lakes in the eastern United States. And it's a pretty small critter. I mean, this is when it's bigger. The quagga is significantly larger than that, but this one mussel can filter a liter of water a day. And by filter, I mean they're pulling out all the particles out of the water column, the zooplankton, the particulates in the water, even large algae, and then they're excreting very, very available nutrients. So they clear the water column of all those particles and allow more light to get to the bottom of the lake, and then those excess nutrients allow algae and aquatic plants to really take off. And so the bottom of the lake ends up looking like a golf course. And I've seen some really good underwater videos showing the same area before and after zebra mussels, and it goes from like a sandy bottom to, you know, this 2-foot-high aquatic plant distribution. And because they filter out so much water and they can occur in such densities, they can occur in densities of 100,000 per square meter. So that's 100,000 liters per day filtered, the water filtered, 100,000 every square meter of a lake. That's a tremendous filtration capacity. So that's removing the organisms that young fish need to eat. So anything that's dependent on zooplankton is going to have a real problem. So you see crashes in the fish populations and just complete alteration. You wouldn't hardly recognize Flathead Lake if this guy appears. And the shoreline becomes coated with these really sharp shells, and so people tend not to use the shorelines anymore. And I just threw this in because I wanted you to realize that invasives can really get a start in these sorts of developments. And I've tried to talk to a lot of local folks about this because it's been shown in other areas. The water warms. You have a lot more nutrients in these sort of situations because there's not a lot of buffer strips, and often they're in developments where there's fertilization going on. So all of those things added together, warmer temperatures, more nutrients, it's a really good place for non-natives, plants as well as other critters, to get a foothold and then move out from there. Another potential problem that still remains in our catchment and elsewhere across the U.S., of course, is stormwater drainage. And this was a real eye-opener for me. I worked on this study in the late 90s, and I was so surprised to see that stormwater outfalls are going directly into our rivers and streams without any treatment whatsoever, some of them. And they're making a lot of strides now in the Upper Flathead to improve this. There are a lot of water districts forming and watershed groups trying to improve this, and the city engineers are trying as well. But just notice a lot of the different constituents that exceeded EPA benchmarks for stormwater, including VOCs. And I didn't even put up here the really scary table of all the 2,4-dibenzyl toluene whatevers. I mean, there was some really nasty stuff in the stormwater. I was really surprised. Besides the lead and the zinc and nitrate and volatile organic compounds. And hopefully we've put this threat to rest. Cabin Creek Coal Mine and others that could have potentially put selenium, nitrate, and sulfate values way above our background levels in the Flathead. So hopefully we don't have to worry about coal mines in the Upper Flathead anymore. And I have to say something about non-point source pollution. It still remains a concern where we have a lot of development going on. A lot of groups really pushed hard in the Flathead to improve water quality by enacting some new regulations to increase the size of buffer strips. And they were really put down pretty hard. And though some protections were put in place, they really weren't sufficient. And you still, this isn't anyone on Flathead Lake because I didn't want to receive hate mail or whatever. So I grabbed this off the web. But there are plenty of these kind of sites around Flathead Lake where you just have grass between a large impervious surface area in comparison to the land on which it sits and a nearby water source. Grass does not constitute a buffer strip. A buffer strip is native or some other vegetation that doesn't require a lot of watering, and hopefully in the future no watering and no fertilization, so that it can take up, adsorb, and hold the nutrients coming down in precipitation and store it and keep it from flowing into the water body. And it's needed in agricultural areas as well. And you can see a really nice buffer strip was created along this same corridor. And I have to mention climate change. Certainly that portends to throw another really interesting dynamic into the whole Flathead food web scene. So I thought I'd tell you just a little bit about, and this is my last sort of technical slide, and then a pretty picture of Flathead Lake. So this shows, each one of these lines is the temperature in Flathead Lake in degrees centigrade for a whole year. And these are called isopleths. And so if you look from the surface down to the bottom of Flathead Lake in the middle of summer, you see it's warm up here and cold down here. And this area in here where the lines are close together and horizontal, that shows thermal stratification. There are really big density and temperature differences that isolate the upper warm waters from the bottom cold waters. They're circulating but not between one another. And this is real significant because Mysis relicta doesn't like to pass beyond 15 degrees centigrade. So it's going up and down like this, coming up here to feed where zooplankton are, and then going back down here at night to sit. And it doesn't like to go up into this region. So zooplankton, those that will migrate, are finding a refuge from the mysis by staying up in this warmer area and not going down where mysis is. And this area in Flathead Lake is increasing because it's warming earlier in the spring and it's staying warmer longer in the fall, and it's getting deeper, this warm area. So that refuge is increasing. That refuge that mysis, that zooplankton will have from mysis is increasing. But that increasing area of warmer water also means there's more area for algae to grow faster, and the warmer water is going to increase that ability as well. So complex changes both to the food web and to nutrient cycling from changing climate can be expected. So we're kind of looking forward to that. So of the 300 large lakes of the world, Flathead Lake is one of the cleanest in a basin that has a lot of people living in that basin. And Flathead Lake's saving grace really is that such a large percentage of the catchment is in wilderness and protected forest lands, and that there are no big polluters, there are no big industries in the Flathead, and the human footprint is relatively small. So you can really think of Flathead Lake as a wide spot in the river. And so that old adage that the solution to pollution is dilution is somewhat relevant. And as long as we are good stewards in the land and the catchment, what we see and what we do in the catchment upstream of Flathead Lake is what will be reflected in Flathead Lake. So I'll take any questions. Thanks. A lot of people helped.
Questions for Bonnie?
Surely there's a fisherman who wants a new fish. Yes.
You were saying that Mises was feeding the lake trout every year at the bottom of the lake?
Pardon me? The
You're
last.
saying that Mises were feeding the lake trout at the bottom of the lake?
Yeah, the juveniles. You know, mysis doesn't just sit on the very bottom, but they do stay down in that dark zone. And there have been some recent studies using acoustic Doppler profilers that's finding that they actually hang out in layers above the very bottom of the lake. So as long as they stay in that zone that is not lit, where there is no light, they're not going to really be preyed upon by those sight feeders like the pelagic kokanee.
But the lake trout are eating.
Yeah, oh
They're
yeah.
not sight feeders. They're what? Filtering them down there?
Well,
They can see.
they can.
Yeah,
He said they key in. Here's a excellent fisheries person here. I'm more of the food web gal, but he said they key in on them as well, so they can see them too. But the juveniles, I'm sure they're feeding right on the bottom. These guys, they're just coating the bottom. If you can imagine 125 in every square meter. And now the numbers are, I think last year they were up to 92. So every square meter of lake surface, you can imagine on the bottom, you're going to find 92 critters of this size. So pretty easy to bump into if you're hanging out on the bottom.
I think it's called Hoover vacuum type feeding.
Might be. Yes.
I came in a bit late, so I apologize if you already answered this. I can just find out later, but what are the current management plans on the table for Flathead Lake and current invasive species?
I don't know. Has Karen already spoken, or is that later in the session?
Karen spoke yesterday at the round table, so.
Okay. There's a big committee that has formed in the Flathead, a technical working group that's meeting, and we're trying to get a lot of signage up, a lot of education, people at the boat docks where people are, coming from other regions, so that we have volunteers checking boats. We're trying to get a couple of wash stations to disinfect boats that have come from elsewhere. And you can talk with Karen Miskey is here from the Flathead Basin Commission.
Is
She can
Karen
tell you
here?
more about it.
Karen, yeah.
Karen, you want to add something?
Raise your hand, Karen, so that Jennifer can see you.
Mm-hmm.
We're hoping for the next couple of weeks, actually, that we'll have PFAs running in Lake County, Flathead County, and Missoula County. So that hopefully will kind of off the release species. And we're in the process of finding out now what other funds will be available for this field season in terms of school check stations. Cool, thank you.
So there was willingness to adopt an aquatic invasives management plan, but still resistance to streamside and lakeside buffer zones.
Yes.
Sad to say.
Property rights.
So one more. See a hand, another hand up out there? I guess they have withdrawn that question. So we will thank
Thanks.
Bonnie again, and we'll move on to our next speaker. And our next speaker is Will McDowell, and Will has been involved in all sorts of sustainable development enterprises around the world, and his expertise here with respect to the talk he's giving today was that for 10 years he was the coordinator for the Voluntary Nutrient Reduction Program, working with the Tri-State Water Quality Council. He is now working with the Clark Fork Coalition, I believe is their Upper Clark Fork Restoration Coordinator. Is that correct? And I'll let him just pull up his presentation here. He's probably faster at it than I am. But I set down my papers.
How does this go?
You can adjust that.
Okay.
You can karaoke it if you want to.
That was a really great talk by Bonnie. I feel like we all should get some kind of continuing education credits in freshwater biology after that. That was really wonderful. No, I loved it. I'm going to talk about a program to try to address nutrient-related problems, somewhat similar to the problems that Bonnie was talking about in Flathead Lake, but in the river ecosystem of the Upper Clark Fork. And this is a really more talking about the management side of things, how this problem has been addressed over the last 20 years in the Upper Clark Fork. And as Vicki mentioned, I worked for 10 years as a consultant to the Tri-State Water Quality Council, which is a collaborative group working in the whole Clark Fork River Basin on water quality issues, particularly on nutrient-related issues. The VNRP, or Voluntary Nutrient Reduction Program, was, as I said, a collaborative effort, but it was also done within the context of the TMDL program that Mark Kelly introduced, the state of Montana's water quality program, and it was the first large TMDL developed for the state of Montana back in 1997-98. The goal was to restore the beneficial uses and eliminate nuisance algae growth in the Clark Fork River from Warm Springs Creek there in the Upper Clark Fork to the Flathead River confluence. This TMDL process was done through a negotiation. There's a number of major players who I'll mention, but there was a 4-year process of intensive negotiation to reach the agreement which resulted in these management, in this whole management program, and that was a really interesting process. I came in right as that process ended, but a number of people, including some here in the room today, were involved in that negotiation to try to reduce nutrients in the Upper Clark Fork through a voluntary process, rather than a process where DEQ or the state would come in and impose limits on dischargers. So this was an interesting and innovative agreement at the time. The agreement now is completed, and this is really a final report on what was accomplished in those 10 years, with a little bit of a retrospective of the 10 and 15-year history before that. So we're kind of looking at a 20-plus year time frame of what's been going on in the Upper Clark Fork. As you can see, we're looking at the same geographic area where the whole Superfund program is going on. And so I kind of think of the Superfund program as a very big kind of marching band, and the VNRP program is kind of a very quiet, maybe flute player tooting in the background about another major problem in the Clark Fork, but not one that had the same importance in terms of toxic materials affecting the ecology of the system, but nevertheless a major threat to the ecological integrity of the Upper Clark Fork River. These data are just shown in a color symbolic format to show you where some of the problems with nuisance algae were located in the Upper Clark Fork. You can see the green line starts at about Warm Springs ponds. Actually, Silverbow Creek has had a very severe nutrient problem as well, but that wasn't part of the work area that we focused on in this 10-year program. So we focused on the area from Warm Springs Creek downstream. You can see the bright green area is the area where there were relatively high phosphorus, total phosphorus concentrations in the river, and that is pretty much identical to the area where there were major algae problems, nuisance algae problems in the river. Although I'm just showing this graph as an example, the same as Bonnie mentioned for Flathead Lake, nitrogen is also a big part of the nutrient problem in the upper Clark Fork River. Both nitrogen and phosphorus as nutrients contribute to the problem. Then as you go downstream past Garrison and Drummond, you're still in a pretty high phosphorus area. As you get flows coming in from Rock Creek, there's a dilution effect and the nutrient levels go down. You're improving towards closer to a not down to the level of less affected rivers like the Bitterroot and Blackfoot, but closer. Then as the Blackfoot comes in, you have further dilution and fewer problems with nuisance algae in that short stretch between the Blackfoot and Missoula. And that's also an area where the total phosphorus concentration tends to be lower. And then when you get downstream of Missoula, you have Missoula Wastewater Treatment Plant discharging one of our biggest discharger of nutrients, and there's another problem stretch downstream that goes for a number of miles, and then through dilution, the problem starts to resolve itself in the Middle River. As we looked at what we were going to try to do starting in 98, 99, it's really kind of daunting. And the reason I put this slide up here is because if you think about it, you're talking about an 11,000 square mile watershed, and you're trying to affect the nutrient balance in the major drainage of that entire watershed through a relatively modest program that had just a scattering of different sources of funding. There was no major source of funding like a Superfund settlement with a responsible party to fund an ambitious effort to change basically the nutrient concentration in this whole river system. And so I looked at it as a very ambitious and daunting prospect to try to meet these goals. And the goals or targets were, in one case, the algae targets, reduce the amount of algae growing on the rocks on the bottom of the river, and number two, and probably the only thing that we were sure that we could directly affect was the nutrient concentrations in the water column. And so these goals were set, and they are substantially lower. These nutrient targets are substantially lower concentrations than the concentrations that we started with in the late 80s and early 90s. So it's quite a process. But as you can see, luckily there's somebody down there below who is monitoring the situation. So we're going to determine whether or not this process is really going to work. The nutrient dischargers who were most important in this whole process, who worked for years together in a collaborative way, and I think in an exemplary way, were Butte Wastewater Treatment Plant, the public works of the city of Butte and Silverbow County, Deer Lodge, the city of Deer Lodge and their whole wastewater treatment program, Missoula Wastewater Treatment Program, the Missoula County Health Department Environmental Health Program, and Water Quality District, which worked intensively on reducing the impact of septic systems on the river system and the groundwater system in our area, and Smurfit Stone Container, which was a player and a key collaborator from the very beginning of this program. Of course, there's other sources of nutrients in the basin. Non-point source nutrients are very important, and there's also smaller dischargers in the basins. I mentioned some of the small towns there that have wastewater treatment plants. But those minor point sources were not directly involved in the VNRP agreement because the early science showed that the majority of the summer nutrient loads, the soluble nutrient loads, were coming from wastewater treatment plants in that first list of the cities and, in one case, industry. So I'm going to show you a series of different graphs. I'll probably run through these quickly, but just to give you a sense of the long-term effort to reduce nutrient loads by the different municipal and industrial entities in the Clark Fork Basin. This is Butte wastewater. Unfortunately, Butte was the one that didn't have continuous long-term data for the 1990s, but actually from about 1989 to 1997, where this graph begins, there was a significant reduction in phosphorus discharge from Butte wastewater treatment. That's not shown here, but I'll remark on where that came from as we look at some of the other towns. This is Deer Lodge, and you can see kind of a continuous effort from 1989 through about last year or year before last in terms of the amount of nutrients that they're discharging, and a whole variety of different programs affected that. One of the programs was the same type of thing as was done in the Flathead, where there was a ban in 1989, first in Missoula, on phosphorus in laundry detergents, and that made a big impact early on in the program. Unfortunately, that was about the same time a lot of the monitoring started, so we didn't always bracket that and don't always have a good sense of how much impact that made, but in some of the sites we do, and it was very significant. This is Missoula wastewater treatment plant summer nutrient discharge to the Clark Fork, and you can see through history what was happening as Missoula started to connect more and more of the outlying areas to the wastewater treatment plant and put those areas on sewer. What happened is they assumed a much greater load of nutrients coming in to the wastewater treatment plant. You can see that in that time period, 98, 99, 2000, 2001, for example, in the total nitrogen, quite a spike upward in the total nitrogen that they're discharging, and that's because they're absorbing a much greater load as they connect hundreds and hundreds and hundreds more houses. Why doesn't the phosphorus show the same spike? It's because at the same time they were doing management changes to their treatment process that were reducing the phosphorus concentrations in their discharge. And then you can see in 2005 there's a very dramatic drop in the total load of nitrogen discharge from the system, and a very significant drop as well in the phosphorus. And that is when the biological nutrient removal program came online. That was an $18 million investment by the city of Missoula. All of you who live in the city of Missoula and pay sewer bills are partly responsible for that, so give yourself a hand for making a huge investment that, as you can see, made a huge difference in the amount of nutrients being discharged right into the Clark Fork River. Missoula City and County had a much more complex task to take on. They took on the task of trying to reduce the amount of septic systems that were leaking nutrients into the shallow groundwater, which were then discharged into the river. And you can see over time, such in the second bullet, or the first bullet, over 3,000 existing homes in a 10-year period were connected to the sewer, and then that effluent was then treated by the upgraded plant starting in 2005. This whole program reduced nitrogen discharge to the aquifer by over 200 pounds a day, and much of that goes into the shallow aquifer we know goes directly into the river, where the aquifer in Missoula, the valley aquifer, discharges mostly into the Bitterroot River through shallow groundwater discharge. If you walk along the Bitterroot River in summer, you can feel cold water springs in the shallow water on the east side of the river, and that's the aquifer discharging directly into the river, and that was carrying quite a nutrient load. This is Smurfit Stone Containers efforts over this approximately 20-year period, and they started back in the 80s and 90s. They were actually adding nutrients to their effluent to try to digest some of the components in their effluent. They adjusted that program. They made multiple adjustments to their industrial process over the years, basically what I call becoming a cleaner and cleaner industry just by adjusting their internal processes, and resulted in a dramatic reduction in the discharge of nitrogen and phosphorus to the Clark Fork River over that whole time period, which is displayed here. So let's summarize what the dischargers were able to accomplish, and I wanted to look at this in a 20-year time frame because a lot of the work, starting with some of the bans on phosphorus in in laundry detergent, and some of the wastewater treatment plants really started working on this problem as soon as it was fully recognized in the late 80s and 90s that we had a very enriched nutrient situation in the Clark Fork River. So looking at it on a longer time frame here, you can see what they were able to accomplish. And just looking at the last two columns, you can see what each one of the dischargers did. Phosphorus was where they were able to make the greatest progress. And you can see overall Butte, Deer Lodge, both over 50% reduction in the total phosphorus load they discharged into the Clark Fork River system. Missoula, even a greater percentage reduction in the total load, even while the population is dramatically increasing and the number of people hooked up to the wastewater treatment system is dramatically increasing in Missoula. During that time, they're still able to reduce the total phosphorus load dramatically. Smurfit Stone Container also dramatic reductions, leading to a total point source reduction of discharge in the summer to the Clark Fork of 18% reduction in total nitrogen and a 66% reduction in total phosphorus. So in terms of what was set out as goals for these entities in the VNRP agreement, they were able to accomplish a large percentage of their goals of reducing the load of nutrients that they put in the river. And the question then becomes, did that result in measurable improvements in the river itself? And so that will be what I'll touch on next. I don't have the names of all these species of algae, Bonnie, but we have a general idea. The one on the right is, there are two different general types of algae that are common in the Clark Fork River. The photo on the right shows a typical scene in the upper river, and you can see these long strands of algae. These are the Cladophora genus, and it's the dominant species in the upper river, down to about the Blackfoot confluence, and sometimes you can see this coming down into Missoula, but it's much more prevalent in the upper river. On the left photo is a depiction in shallow water of the diatomaceous algae that grows on the rocks on the bottom of the river, and it doesn't have that filamentous type form, but it coats the rocks and turns them green and very slimy and similar in some ways to some of the photos that Bonnie showed of the lakeshore. But these two types of algae, it turns out, are very distinct in the way that they react to reductions in nutrient supply, and we'll talk about that a little bit in our conclusion. But those are depictions of what they do, and ecologically, we don't know as much about how these algae affect the ecology of the river as perhaps we might in the lake, but we know that when they're very dense, they change the ecology of the system quite a bit. The whole macroinvertebrate community changes depending on whether you have a heavy algae growth on the bottom or not. You have potential effects on the oxygen supply at certain places and certain times of year and certain times of day. And you also have a very big inconvenience for boaters and sometimes even for irrigators when you have this huge amounts of what's called slime in the upper river coating your irrigation equipment. So I'm going to show a series of slides that try to collapse a lot of water quality data into a few slides and give you kind of an overall picture of what's going on from upstream to downstream in the river. The 4 points that I picked to try to illustrate the improvements in nutrient concentration in the river are the Clark Fork at Warm Springs on the left, and then moving downstream, the Clark Fork below Deer Lodge near the Little Blackfoot River, the Clark Fork below Missoula, down near right above the confluence with the Bitterroot near Kelly Island, and then the Clark Fork at Huson downstream of Stone Container down near Alberton. So first, let's look at total phosphorus concentrations. Were we able, through the VNRP and associated programs, able to affect the total concentrations of nutrients in the river system? What I did was a little bit different than some of the analyses that were done. PBS&J did an excellent trend analysis of nutrient concentrations. Their conclusions were very similar. Their statistical analyses were far more sophisticated than mine, but I thought it was important to look at the river in kind of a time step, because a lot of the major improvements were not done continuously, but at a certain point in time there was a major investment that made a difference. So I'm more interested in looking at this more in terms of a before-after scenario. In other words, what was it like in 1980, 88, or 88, 89, 90? That is the first dark green bar. Is the nutrient concentrations during that 3-year time period. And then we compare that to another 3-year time period 10 years later, from 1998 to 2000. And then we compare that, and that's about when the VNRP program started. And then we compare that to the last easily available data that I looked at when I put this slide together, which was 2005, 2006, 2007. And each of these 3-year periods then accumulates a number of data points from summer nutrient concentrations. And what I think it shows is that in all 3 areas, or all 4 sites on the river that we looked at, we had some sometimes dramatic decreases in the mean concentration of total phosphorus in the river, both upstream and downstream. When I showed that slide, I really liked it. I thought it was simple. I thought it was a good illustration. And I was really pretty impressed with how it depicted the improvements. And then I talked to our technical committee, and as you might imagine, there's a number of people that think that slides like this are a little bit of happy science and not really real science, because you're disguising a lot of variability in the data set with just taking a mean. So thanks to those statistical skeptics, we looked at a little bit more detail, and I don't think everybody wants to look at all these type of graphs for a long time, but just for the statistical skeptics in the crowd, there are in many of our, if not most of our examples, statistically significant differences between the 3-year data sets as we move forward. And this is just showing quartile analysis with the boxes showing from the 50% middle data set from the 75 percentile to the 25th percentile. At the top is the extreme measurement of the whole sample. In any case, you can see that the medians are declining, and often the data sets are quite distinct from each 3-year data set. Deer Lodge, below Deer Lodge, the phosphorus concentrations are even more dramatically different in each 3-year time period. In Missoula, we didn't have much change in the first 10-year period because of all that increase in population being put on the sewer without commensurate upgrades in the sewage treatment program. But from 1998 to 2005 and 7, we have some pretty dramatic differences statistically in the amount of total phosphorus in the river. So then we look at nitrogen, and again, this is my happy science view of what happened over 4 sites over the 20-year period. And again, in most cases, we see declines in the total nitrogen concentrations. You can see a couple examples where the decline isn't as convincing, and certainly in Missoula, below Missoula, we haven't had the same magnitude of declines in the total nitrogen concentrations. So statistically, those of you who are interested, I can give you these slides, but there are often pretty statistically significant distinctions in the total nitrogen as well at many of our points. Deer Lodge, not as much in the last 10 years. Missoula, certainly not in the last 10 years. Total nitrogen has not statistically declined that much, and we'll talk about that a little bit if you want to, why that might be. But these type of programs, like the VNRP, these are TMDL driven programs. In other words, they're trying to meet specific targets. And the targets that we set were the ones that I showed at the beginning. And so really what people are interested in is how often are you meeting the targets that you set at the beginning of the 10-year period. In other words, as that stone wheel rolls down the hill, are we surviving or not surviving? Are we making the grade or not making the grade? And you can see the short story here is that in total phosphorus, there's a real improvement in the upper river in terms of meeting those targets, but we haven't met the targets even in the majority of our sampling in the last few years. We still have a long way to go in the upper river in meeting the phosphorus targets. Whereas below Missoula, in the last set of samples, we're meeting the phosphorus targets almost 100% of the time, and the same in Huson down by Alberton. So the lower river is doing way better, but before those of you who live in the lower river congratulate yourself for being better stewards in the upper river, you have to realize that the upper river targets were much tougher. And so they had a much longer way to go, and I think the fact that they are meeting those targets even 40% of the time is quite an accomplishment, given that there was 0% compliance back in the 80s, and even in 1998 there was barely any compliance. So there's quite a bit of progress shown in meeting the targets. Nitrogen targets, the upper river is doing way better. You can see in Warm Springs, they're meeting the targets in the last data set 70% of the time, about 40% of the time in Deer Lodge, and then about 70% of the time in Missoula and in Huson. So you can see the lower river is doing really well on phosphorus, but not as well on nitrogen, and the upper river's a little bit the reverse, doing better in terms of meeting their targets on nitrogen and not as often on phosphorus. Now we look at the algae data, and what we have here is data from 1996, I think, through 2008. But just to give you an idea of the huge variability in how much algae is growing on the rocks on the bottom of the river, this is just above the Little Blackfoot. The blue line is the target that we set, so you can get a sense that there's a very erratic compliance with targets. A lot of the time we're not meeting the targets, and unfortunately in the upper river, the statistical analyses have shown that we're not actually improving our compliance with the algae target yet, even though we made these fairly dramatic improvements in the nutrient concentrations in the river. Below Missoula, there's a little bit better compliance with the target in terms of trying to reduce the nuisance algae to a level that was set. And remember, going back to the slides of the two types of algae, again, the upper river and the lower river are kind of apples and oranges. You're talking about two different types of algae, and it turns out that the type of algae, the cladophora in the upper river, is much more difficult to control by simply dialing down the amount of nutrients in the river. It's not nearly as easy to do that, and that's ecological complication that we're dealing with. But the statistics done on this data show that there is a small improvement in the algae concentrations on the bottom of the river over this 13-year time period. At Huson, you can see they weren't really suffering too many problems even in the past, but certainly the frequency of problems has gone down. So again, the lower river seems to be on an improving trend in terms of meeting the targets. So this is just the statistics there. You can see the algae density trend in the upper river at Little Blackfoot is still increasing. And that's an anomalous result, perhaps, but there's a lot of factors that go into growing algae on the bottom of the river other than simply the water column nutrient concentration. So that's somewhat discouraging after all the great work that's been done. But again, we need to understand the ecology of the situation better and see over the long term whether that trend turns towards an improvement trend. The algae density trend in the lower river was statistically significantly decreasing, so that's a positive. At Huson, the trend really was not significant either up or down. So here's some conclusions, and I'm finishing up, and I hope I'm on time here, Vicki. The signatories over the 10 years really made, I think, tremendous progress in decreasing the nutrient discharge, the pollution discharge into the Clark Fork River by decreasing nearly 10% closer to 20% in total nitrogen and 60 to 70% in total phosphorus, their nutrient discharge. The river concentrations reflected that. Many people questioned at certain points in this process whether a strong focus on point sources was really the right way to go, or whether we should be putting more effort into non-point sources. But I think we can see from this data that the effort in decreasing discharge into the river from point sources really did make a difference in the nutrient concentrations in the water column in both the upper and lower river. The algae concentrations are responding somewhat in the area below Missoula, but not responding very well in the upper river, and are not really statistically changing in the lowest area down by Alberton. The nutrient targets set in 1998 appear, after a lot of scientists have looked at them, to be pretty good and to correspond with actual levels of algae in the river. The state of Montana is setting nutrient and algae standards right now for surface waters, and they're using this Clark Fork experience heavily in orienting their work, and they feel that the approach that was taken back in '98 still appears to be a reasonable approach to trying to control nuisance algae through nutrient concentrations. As we mentioned before, the type of algae, Cladophora in the upper river, is really difficult to control. Walter Dodds just helped us out by doing a scientific review of our work a number of months back, and he found that the Cladophora in the upper Clark Fork is actually more productive and relative to the concentration of nutrients in the river. It's more productive than almost any other river he's ever looked at. I don't know whether we've created a new super Cladophora in the upper Clark Fork through various processes, but he says it's outside the bounds of the other areas and the other rivers he's looked at, and he's looked at rivers throughout the entire world where Cladophora grows. So we may be dealing with a particularly difficult situation up there, and we need to know more. So that's what I had. This program, VNRP, was a collaborative process. There were huge contributions financially and time volunteered over a very long period by a lot of people, and some of them are mentioned here, not all of them, but certainly the municipal governments. I want to make sure we recognize Smurfit Stone Container was involved in this program from the very beginning, did a great job. City of Deer Lodge has been a real strong player. They're still dealing today with some major issues with how to upgrade their wastewater treatment plant in Deer Lodge, and they have some big challenges there. Grant Corrs Ranch, the Clark Fork Coalition, University of Montana, Vicki Watson was instrumental in this program from way back at the problem identification stage all the way through. Missoula County, the Missoula Water Quality District, Butte Silverbow, some of the engineering firms, Missoula Wastewater was fantastic, and their lab staff did a lot of the analysis here. We also did work with DEQ. A lot of people question, as I said, whether or not there's enough work done on non-point source pollution control for nutrients, and actually we did some summaries, and DEQ invested over $3 million in the upper Clark Fork, including the Blackfoot and Bitterroot, over the last 10 years in programs that were non-point source pollution oriented, and some of those were studies, some of those were on the ground projects, but DEQ's 319 program has been extremely active in trying to help address this problem. That's what I've got, and again, I want to recognize Tri-State Water Quality Council, who coordinated this whole effort. Thanks.
One very quick question, and then I'll ask the rest of you to save yours and catch Will during the lunch break.
Will, given that algae is affected by temperature, and also
It looks like the deletion's a huge factor as you go downstream. Are there any projections for slightly warmer temperatures and drought? If you have a little less water and a little higher temperature, what's going to happen to nutrients and algae?
I haven't seen any scientific projections about that. But as you imply, there's some concern there. Sunlight is key in terms of, and temperature is also important. I think the frequency with which there are floods that scour the bottom of the river and set that algae back to, especially in the upper river, but also in the lower river, set the algae back to growing from scratch rather than being able to grow from the status that it ended in the fall and start back in the spring. If it's a very vigorous plant still, then it's going to cause a even greater impact. So whether or not we have scouring flows is a really important factor, but we don't have all the pieces of that ecological puzzle put together, and I don't think that anybody's got a prediction model.
I predict there's going to continue to be clitophyra in the upper river for a long time. It loves the upper river. I guess it decided once it learned to live with copper, it could stand anything. So just before I bring our last speaker up here, in the event that the people start trickling out, I do want to urge folks to finish off the muffins and to remember that those who purchase lunch tickets, the lunches are down, you go out the hallway and towards the south and through some doors and around where you'll find the posters and displays, and the lunches will be there. And please, those of you who bought lunch tickets, grab your lunches right away, because at about 12:45 or 1 o'clock, if there's a bunch still laying there, I'm going to turn the ravening hordes loose on them so that there's nothing left over. If you are a presenter and you haven't yet sent me your presentation, see me at the beginning of the lunch period so that we can get you loaded onto the laptops. One of the sessions, the session dealing with the whole basin, will be meeting in this room at 2 o'clock. And all the other sessions will be in the little meeting rooms that are down by where the posters and lunches will be. They'll start at 2 o'clock. The poster session is our lunch break from lunch till 2 p.m. And just before we break for lunch, I will do another raffle drawing for a fabulous prize, just to try to keep people here till the end. And there will be another drawing at the very end, when we sort of come back after, for those who wish to do so, we'll have a little final roundup session back here at 5 o'clock, very brief, where the moderators of the different sessions will tell us 2 or 3 exciting things they learned in their sessions. We'll do one final drawing at that time. The raffle includes tickets to the Living Downstream film documentary premiere at the Wilma tonight, and some other fun things. I'm afraid the Rock Snot T-shirt got snapped up last night, but there are some other fun presents in the raffle. And if you haven't put into the raffle yet, you still can, as long as you have brought your very own refillable water bottle or coffee mug today to reduce waste. You can throw your little raffle ticket into the raffle. So our last keynote speaker this morning is John Sesso, who is, I believe, the head of the planning department of Butte-Silver Bow County. He also represents that area in the state legislature, and he is going to talk about 25 years of trying to clean up Butte. And I believe that people have been trying to clean up Butte one way or another for a very long time, but this latest effort seems to be one of the more successful ones.
I don't know how to tighten this, but well, good afternoon or morning. I would like to thank you all for inviting me here. I would also especially thank you for getting me out of a Legislative Finance Committee meeting today. They were taking the final vote on what all the money we were going to cut out of the state budget, and I was glad to not be there for that particular occasion. I also am very thankful to be part of the symposium. It's been a few years, many years, since I have participated in the symposium, but the good news is I'm here, and the upper river is being represented. The bad news is I'm here after 25 years. I see several of you who were there in 1985, and it's just a little bit of reality to know how old you actually have become after all these years, and that's very depressing to me. So anyway, I'm just going to do a... That would be easier. Thank you. There's a couple things that I am going to try to cover today, and a couple things that I am not, and I thought we should go over them. Of course, I'm going to concentrate in the area right here in Butte. I trust that Joel and the paper on the Silverbow Creek project has been covered, but a very important project that has produced many significant results. I'm also not going to be able to talk any about Anaconda, and of course the focus of your symposium from Deer Lodge down is, I'm sure, been covered very well. But we're going to concentrate to a few minutes here in the Butte area. The couple other things I'm not going to cover. This is what we call the Butte Silverbow Priority Soils Site. The site is our area here in Butte, but I'm not going to say much today about the Berkeley. Very big deal in Butte, probably the worst environmental threat that we have. That's got its own operable units, got its own set of parameters, and I could talk a couple hours on that site, but I'm not going to today, and I'm not going to talk about the Montana Pole site. These are separate sites that were addressed in separate legal and technical means over these last 25 years. I'm going to concentrate on what we call the priority soils site, and it's about 5 square miles. It affects the communities of Butte, and this picture gives you a sense of how our site really different from Silverbow Creek, and then what we're doing with the Clark Fork and what we've done with the dam is a little different in the sense of all of the site's area is totally integrated with the community. I mean, this is where people live, this is where people work, and all of these sites, the entire site is right next door, and of course it's right next to the Berkeley as well. So it's created some significant challenges to try to deal with remediating a environmental damage right where people live and work. The site really is about 3 main goals. This is my own non-technical description of what it's all about. It's about soil and water, just like most Superfund sites. Here we had 3 principal goals, and that was to eliminate contact with contaminated soils and dust in residential properties, and to remove or cap contaminated soils, and primarily the removal of these contaminated soils was all about preventing exposure to the stormwater coming off that hill. If you just take a peek here again, from the top in Walkerville to the bottom, this doesn't seem to be working. Down in here is the lowest spot, about 5410 elevation. Up top it's closer to about 6410. So there's about 1,000-foot drop from the top to the bottom over a course of approximately 1.5 miles. And when you're trying to basically get people, or get these soils in the day, all of these areas were just as contaminated as can be, and it was all about covering them up or removing them so that the water flowing over them would not reach the receiving stream of Silverbow Creek. And then lastly, not only the stormwater, but the groundwater is a particular problem where the bedrock aquifer in the areas surrounding the pit and really up in here have pretty much been written off because of the environmental damage. The alluvial aquifer coming through the bottomland in the Summit Valley and the Silverbow Creek, the historic Silverbow Creek drainage, is still very much in play and a resource that we can protect and improve. But that's about the tall and short of our endeavor, And that's what we've been working on for these 25 years. Each of these little purple boxes represent a Superfund cleanup in and of itself. Unlike most cleanups where you wait till you make a decision and then you get going on the cleanup, Butte was a little different because starting 25 years ago, there was just a lot of things that were just very evident that we could get done, whether it was a Walkerville cleanup or on Timber Butte. Each of these areas I'll show in a little more detail. But we've been at it for a long time, and each of these come with an investigation, come with a feasibility study, come with an action plan, come with a remedial action. And so by the time we got to 2006, when the Record of Decision came out at that time, a lot of work had already been done. And I think that that's worth noting as we go through this particular site. This is somewhat typical of what kind of soils exposed we had. This is at the top, right above the Walkerville dump, place called, we call the Granite Mountain Memorial Area. And it was very interesting when you come to town. I moved to Butte in 1978, and these piles and these dirt piles are right in, next to people's houses. I mean, this was the environment in Butte before Superfund, and like I said, we had to address these contaminated soils primarily to keep rainwater from picking up heavy metals. But more direct issue with human health as opposed to environmental health was our multi-pathway lead poisoning prevention program. And in this case, it was a challenge to really parlay Superfund law with how people were really getting sick. The bottom line was that Superfund allows you to remove contaminated soils, and in the early 80s, our studies showed and our blood testing showed that we had children that were in excess of 10 micrograms per deciliter, and more than 5% of our population, and that puts you in a category of having to take direct action. What we realized, though, in then starting to abate the environments where these children were sick, was that it really had less to do with soil and had more to do with their living environment, and a lot of lead paint that had actually made them sick. And so we were able to design a program where we tested, and all these green dots and everywhere you see, some 1,000, 2,000 tests where we had elevated soil lead. We did not have a corresponding elevated blood lead in children. What we had were elevated blood leads in areas that weren't necessarily where we had elevated soil lead. So we thought it would be better to set up a program where we prioritized what we should do, and we managed to convince Tharco to give us a good bit of money to implement the multi-pathway approach, so we could get the dust, we could get the paint, we could get the water pipes made of lead, and we could concentrate on where the children lived. And we do this in a sort of a coordinated fashion. We used our technology to track everybody's houses, and we do the sampling. We match up their houses with their blood leads, and we get right after where they live. And this has been our priority. It's been our system since the mid-90s, and we're very pleased to say that where once we had a population of in excess of 5% of children with elevated blood leads, we are now down to less than 0.5%. We basically have, 4 or 5 kids every year that are continuing to show up out of a couple thousand, and then we are able to get right after it. So the challenge with this program has been to convince the authorities to allow us to use the Superfund resources that are designed to remove lead to get at the attics and get at the indoor environments where people were really turning out to be getting sick. We basically remove the soil lead from people's yards, and then we have the resources to come back and give them a decent yard, and then we go into attics and sample first, and then if we find elevated levels of arsenic and mercury, then we basically own these big vacuum cleaners for all intents and purposes, HVACs, and suck all the dirty dust out of the house, and do that as part of our program. The second part that I talked about is the source areas. There were some 300 distinct areas in town where basically rainwater would just roll over the dirty dirt and find its way into Silverbow Creek. Our basic program is to those sources that are very high in heavy metals, we remove the waste completely, bring back clean materials, and then revegetate the area that we've impacted. Some areas are not that bad. They still have the opportunity to contribute metals into the creek, so we just cap them in place, bring in a lime layer, and then 18 inches of soil. And the biggest challenge we have now, we've pretty much addressed all of these 200 sites. They're all capped. The challenge for the future is to keep them that way and to monitor their surface, make sure that there's no re-immersion of waste, there's no resurfacing of waste, and that we keep the revegetation and the plants in good shape over them, so we continue to eliminate that exposure for the long term. We think that we should be able to do that. The local government has agreed to do that. We believe the local government has the highest and greatest vested interest in making sure this works in the long term. So we felt that it would be prudent for us to take on that responsibility, and I think it's worked pretty well for the first 15 years, and it should work fine for the next 100. This is just a map that shows each of the specific areas. Each of these polygons represent one of these 200 sites that had to be either removed or capped, from the tip of Walkerville up on top, and the Alice Dump and the Alice Pit area, all the way down to Timber Butte on the bottom. This is the low point in the valley. This is where all the stormwater collects. But each of these areas had to be capped, and now is being managed under the program that I described. This is the top of the hill. This was Timber Butte, as I mentioned, looking down and then back up. So you can see the topography. This is the low point again. This is back up the hill. This is the site of the old Clark tailings. And this was one of the first cleanups in 1990 up and around. This was the last remnant of the old Clark mill. It was a zinc mine back in the day. They dumped all their tailings in this area here, but up above and then down below. This was one of the first emergency responses that we did. This shows that the last picture was taken from right about here, and this shows what this looked like in the mid-90s. It was a sort of a giant cesspool of contaminated waste. What we did was we brought in the Colorado tailings. If you look at this area here, this was one of our most and worst areas of contamination, particularly near water, which is the big problem, groundwater and surface water. So we took the Colorado tailings from here. We moved them on top of the Clark tailings to provide some measure of a thickness to eliminate exposure to the bad dirt, and then we built this facility on top of it. And as I'll mention later, an end land use we think is just as important to the cleanup activity. Unless we have the end land use in mind, we feel that we are not going to have as much luck taking care of the place in the long term. So we built this this field, this complex. And so here's another area in East Butte. Again, it was an area that was originally slated to be eaten up by the pit. In the mid-60s, they took a lot of these areas. The Anaconda Company bought and removed several homes because the pit was going to just expand westward. Well, then the pit never expanded, and this area was really left to really die. Since then, we have done several developments, including a big sports complex here. And as you can see, the office, this is an office building that was built in the last 5 years in an area that was completely contaminated in the past, up along East Park Street. These areas have all been rehabbed through the Superfund program. This is an area that's in the northwest, sort of above and to the north of the Berkeley. Again, an area that one of the early pictures I showed, from very contaminated soils and the like. And we built a memorial. We call it the Granite Mountain Memorial because right here we built a memorial for the greatest underground mine disaster in the history of mining. Several 108 guys lost their life in that fire at the Speculator fire. What the Speculator mine is actually right about here. So from the memorial, if you haven't seen it, it's a nice little tribute to those guys. But on the way from town, this will all be cleaned up and paved this year finally. But this was one of our most recent reclamation projects and reflects kind of some of the lessons learned. This is a road into the memorial, and this is a trail from the memorial that connects with several pedestrian trails throughout town. These are just a couple pictures of the way it was and the way it is now. This is literally the same picture. The same area. This is what we faced when we started the Superfund project in the mid '80s. This is typical of a cap. This here is a abandoned shaft. We have a safety fence around it, but that was the site of the Buffalo back in the day, and then they just dumped their tailings right out the back door of the mine, and that's where it stayed from whenever this mine started in the early 1900s to 1990. And so we have been systematically finding, it certainly doesn't take much to find, but identifying these sites and then either removing, and in this case we removed a good bit of the waste and then capped it after the construction. Another view of the Buffalo dump area just is above that capped mine shaft. This was literally the picture before we started and the picture that we have taken since. A couple other areas. These are just all typical of these source areas that we have addressed over the course of the last 20 years. Different areas. This sort of drifts into the next section on stormwater control. This was what it looked like. This is the main gulch coming from the Lex head frame down through one of our bigger valleys, and it's been completely recontoured. Heavy metal contaminated soils removed and now capped. We'll see some other pictures in a minute. Again, just to give you a sense of two things. One, how exposed mine waste was in town and what we've done about that, but also to just reflect how integrated the contaminated areas are with the people who live in the community. The stormwater challenges, as I mentioned, about basically not letting contaminated water reach Silverboat Creek. The system, the solution, the remedy that has been selected is to build a network of ditches and set basins up top on the hill, collect the stormwater, particularly in major storm events, and then let the metals drop out and allow the clean water to proceed. We are using, the second bullet is after we built these Superfund structures, now it's a matter of fine-tuning it. I think that when Peter and several came over 25 years ago in 1985, a good friend of ours, the guy who ran the water treatment plant that Will talked about, when I came on at the government, he said to me early on in the Superfund process, when it rains in Butte, the whole valley goes toxic. It just happens. It doesn't matter if it rains an inch or it rains 5 inches from the top of Walkerville all the way to Warm Springs Ponds. It's just a toxic flow. And it took me a while to realize that he wasn't kidding. He meant every word of it. And what we did was try to eliminate that pollution from reaching Silverbow Creek. And if back in the day, 25 years ago, just for the sake of comparison, 100 units of pollution were reaching Silverbow Creek, I'd say that we're already at the 90% level, and now we're ratcheting down that last 10%. We're very proud of what got done in these last 25 years. We're not all the way there. And the big change was that in 95, we told anybody who wanted to listen to us that this problem is not going to be fixed unless you also deal with the municipal system. The fact of the matter is, no matter how many Superfund structures we built, for example, I showed you a little bit before. This is what it looked like in 95 coming through. This was the Lexington mine on Main Street, and this is the Missoula Gulch. This is the main gulch in town, and the main transporter of dirty dirt and heavy metals from the top to the bottom into the creek below. And since then, as I showed you before, we made quite a bit of progress, not only covering and eliminating exposure to the mine waste, but building these concrete channels that collect the water in these directions. And this is the first of our solutions, and that is to use the syndicate pit to collect all of this drainage into this area. Again, we let the metals drop out, and then we move it from here down to Silverbow Creek. The issue is, though, from here down to Silverbow Creek, it travels through approximately 3/4 of a mile of the municipal system. Well, that's the same municipal system that was built 100 years ago, and if you would ever like to take a tour of this 48-inch pipe underground from one top to the other, you'll see that while you're walking through it, there's not much of a bottom to it anymore, because the acidic metals had just basically removed most of the concrete structure that was put in place. And so, you know, we started the endeavor. We capped the source areas, we collected the water, we dropped out the metals, and then we discharged down to Silverbow Creek. And the testing of the water here, when we discharged it, actually was more polluted when we got down to the sediment basins down below, because it was picking up metals in this dirty storm drain. And so we indicated that the right solution would be that we have to do both. We have to do better to collect, cover, collect, and then we've got to deal with the municipal system. So we have, this is down below, this is at the bottom, we call it Sed Basin 8. That's at the bottom of the gulch. And this one, and then we have another one right here in the background. Those are the last two that before it's piped to Silverbow Creek and discharged. Again, we're meeting standard at the discharge point most of the time, and it's pretty successful so far, but we have still to ratchet down that last 10% and then to make sure we continue to implement best management practices. By that I mean curbs and gutters, so we can prevent run-on and run-off from not necessarily contaminated properties, but just sediments that do contribute to pollution in the creek. We also have to make a pretty substantial investment. The resources we have available to us now are approximately $20 million to improve the municipal system so that we can take care of that last piece. So any stormwater that is picking up metals and along its transport route can be eliminated from reaching the creek. Butte Silver Bow and our community was put in a tough little spot is because of our stormwater system that named us. We got named as a PRP for this cleanup. That's why we have been more intricately involved than perhaps we wanted to. But the fact is, we were named a PRP because of our stormwater system. Under the law, if you're a transporter of waste, you have to take some responsibility for it. So our responsibility is been to cooperate with the cleanup, also then to agree to help maintain some of these areas in the long term. Again, this is from the west side of Missoula Gulch, looking back down. This is literally, you know, what it looked like before we started, and you can just see how the problem existed. And now, you know, we built the channel. We're collecting the waste. It's run to the collection points much more efficiently, and then we've eliminated that exposure on top. This is not your backyard. These are standards that require a minimum of a 35% cover and a minimum of certain types of species density. We got to just watch our erosion points and also to keep it weed-free so that these species can survive in the long term. Lastly, having to do with the treatment of contaminated water. This has been probably the biggest controversy in Butte. Some of these other things I mentioned, you know, we've kind of worked through. There's a pretty good consensus on what we've got to do, but the business of groundwater has continued to be elusive. I see a lot of people here that know a lot about more of the science than I do, but suffice it to say that there's some disagreement on how best to collect this groundwater and how best to treat it. So in 2004, Butte wrote a position paper on what we thought was the proposed and the best solution for our community for this whole priority soils area. And on groundwater, we took a little bit of a powder, and instead of picking sides on all the warring consultants and government regulators, we just thought we would just set the bar. That whatever remedy you choose, make sure it does these 4 things. That it meets the standard, that when all is said and done, it's not ugly to look at, that since it's going to be right through our town, let's make sure that it's something that is integrated okay. Thirdly, that we wanted to make sure we could use a good bit of this property for beneficial use, and then finally that it was practical to operate and maintain. I would say we're probably in the, I don't know, it's like a game that won't end. Maybe it's best to say we're in extra innings. Whatever they said in 2006 has turned out to be wrong. Now they're trying to figure it out again. I suspect it'll be several years before a final solution on groundwater is picked. But this is the area that is really the bottom of the pipe. It's called Lower Area 1. This is the lagoon system that has been put in place. This is the Metro Sewer Treatment Plant that Will talked about, and this is that Said Basin 8 and then Said Basin 9, where stormwater all comes together. This is a point I really wanted to make, that it's really all about one resource, but there's 3 or 4 different regulatory things going on with respect to trying to determine how to make sure that at the end of the day, right at this point here, the water leaving meets the standard. Make sure that it doesn't have any heavy metals in it, and if Will had his way, make sure it didn't have any nutrients in it as well. This is our challenge. How do we make sure our metro water has less nutrients, how to make sure that groundwater treated through the lagoon system doesn't have any metals, and making sure that the water leaving into Joel's rebuilt Silverbow Creek is not repolluting anything. It's going okay. The groundwater, the good news is that this groundwater treatment system, this is just an example of what the Colorado tailings looked like when we started way back when, and we've got a pretty nice little channel through there now. This system, this is where the Colorado tailings were back in the day. This has been reconstructed with what we call the reconstructed Silverbow Creek channel, and this is the lagoon system. It's a few years old, maybe 2 or 3 years old picture, but it's sort of like this. We got the metro and we got these lagoons. Right here is the discharge point out of the lagoons, and unless somebody can correct me, the water leaving the system does meet standard. It is it's meeting the standard, the WQB7 standard for metals coming out of the last pond. The bad news is that there's about 900 or so gallons per minute coming into the system on a regular basis, and only about half of it gets discharged, and it keeps getting recycled back. You know, it goes from here back to the lagoons and the front lagoons, and so we're a little concerned that might not be a sustainable effort. You know, that if you're treating 900 gallons per minute and you're discharging 450. You know, kind of reminds you of the little rabbit in Watership Down, that they get to hang out and eat the lettuce from the rancher, and they could stay in the system forever and never leave. And from the perspective of the long-term maintenance of the system, it's not necessarily a good thing to be retreating half of your water in a perpetual motion machine if you want to keep your long-term costs below or reasonable. So we don't know. I mean, we seem to do okay, and we are much to Will's satisfaction. You know, embarking on our nutrient reduction upgrade to the plant here in 2010 and 11. We have what we call a mechanical treatment plant. We have the sludge management system where we dry it. We dewater it, and then we move it up to our landfill, and we make compost out of it. And we've got a pretty good system of doing that, but this system here is still a work in progress. We hope that its efficiencies improve, as well as the collection system. That's where there's a lot more indecision right now on, are we collecting all the water? Are we collecting, you know, it's designed to collect 900 gallons per minute, but we get more than that. Now we think that the collection system works so good that it's sucking water from the Blacktail Creek drainage. If you look at you know, this is Blacktail Creek, which comes from the south of town out of the Highland Mountains, and right here they converge with Silverboat Creek that used to come out of the East Ridge, till of course there was a Berkeley pit that interrupted the flow a little bit. But this is where this comes through, and right here is where they're trying to do their best to collect all this water that they treat in the lagoons on the end. And you know, they're just I guess the current theory is that the collection system has created a whole new highway of collection, and water that normally would drain into Blacktail is creeping over and going into Silverbow. So they got to figure all that out. It's going to take them a couple more years at least. They are making a pretty good investment to upgrade this. This has been the world's longest treatability study. It started in the early 90s, and they're still studying whether or not it works. But in any event, now they're coming to terms with it, and they've got to now make it permanent and put some substantial upgrades into the system. The last point I make before my concluding remarks is about beneficial use. As I said earlier, we don't think any cleanup is really complete unless we know that the outcome includes a use of the land that serves a beneficial use. I have examples of the three, but it's really a two-sided mission. One is to make sure we do in fact get some beneficial use out of the lands that are cleaned up. But two, we truly believe that having the land in beneficial use and having a purpose for the community dovetails into the necessity to take care of that land in the long term. As I mentioned earlier, these are a couple of ball fields we put in Missoula Gulch coming down into the area here, the Syndicate Pit. But this area in particular, this was a set of mine source areas, and here we put a dozen homes, and then in the Missoula neighborhood up here on Missoula Avenue, we infilled several more homes, and we basically took what was an eyesore And it's a pretty nice little community, and for the affordable homes owners in this area, they may have an affordable home, but they have $1 million view looking out over the Summit Valley. And these are super insulated homes. They're houses that take a couple $100s a year to heat, and it's been a very successful project, merging the need to save energy with a reinvestment in a reclaimed area. In the old days, when you came to Butte, you knew where the pollution flow started up here on the hill that we called the Alice Dump. Now we call it the Alice Knob Hill Trail area. And they did a nice job. They basically lopped off about a third of the mountain, reduced the slopes, dumped the excess material into the pit next door, and then built a nice set of trails and a picnic area on top. Very, very successful reclamation. Here's an area right there on Mercury Street. I mean, I swear to God, this is flowing right down into the street for 80 years. And then that water got into the storm system and got into the creek. We, instead of just trying to cap it and not do anything with it, Aware decided to build a couple of their facilities after proper reclamation. Here's a site above Broadway and Covert Street. That's literally what it looked like. A guy wanted to put some storage units in, so he recontoured and created what is an acceptable cap for this waste. This was a former site of a dump, right within spitting distance of Blacktail Creek, right in that valley where the lowest water is. Through the Superfund program, we were able to turn this into a visitor center and make it look quite a bit better. And then we talked about the Clark Tailings area back in the day. It was just one of our biggest eyesores, and now it also has a beneficial use. The last slide regarding the trail system, and this gives you a sense of then those source areas I talked about earlier. They have now all been capped. They're now in management, and now we've built a set of trails up through them so the public can enjoy some benefit of the cleanup process. The last set of comments that I have is about the 25 years of history. When I came to Montana, I had just left the University of Wisconsin in Madison, and my college thesis, my master's thesis, was on environmental communications. And the guy I got to study and study under was Barry Commoner, and he opened my eyes and the doors to his archives. And he was the preeminent, the main guy back in the 60s and 70s, a scientist who could take a very complex technical issues and put them in words that the public could really understand. And one of his works is the environmental book, The Closing Circle, and in there is all about everything being connected in this valley. This is the Clark Fork River Symposium, and for all of you and many of you, it's about the river that starts at its headwaters at the Warm Springs Ponds. But for me, the Clark Fork River, the upper Clark Fork River, is about at the headwaters starting coming off of the East Ridge in Butte at a time when there were no environmental laws. Everything is certainly connected to everything else, and we need to keep that in mind as we try to move forward in the next 25 years. It's not only connected physically, but the world we're in the context of Superfund, and now restoration, we're making great strides to make sure that remedial actions that have taken place in the Clark Fork are tied now to restoration actions. And that first law of ecology tells us that we got to redouble our efforts to make sure that we're doing the right thing in that regard. The second one has always come up with respect to in the context of this total removal and where we're going to put the waste. We faced it up down here with the dam, and we moved the waste to Opportunity. Now there's work to create some repositories closer by. We have moved wastes around, but the fact is that it all has to go somewhere, and if you take it from one spot and put it in another spot, you got to take care of that other spot when you're done. And you just got to keep all that in mind when we're designing these solutions. As far as the third law, I would just make an appeal that nature is the best healer. We have made a lot of improvement over these 25 years. And I think that it would be important to let nature take its course now that we've removed a good bit of the sources of pollution. Let's make sure we hold some resources back. Let's see what nature does. I'm sure it's going to both reveal what it can do to heal the river, but also what it can't do. There's going to be some pinch points, and so we should listen to nature as we complete the job that we've started. And lastly, it is not something that we want to talk about, but the reality is that it really always does come down to money. How much does anything cost to clean up? And although we would all want to just set the bar and say, okay, that's what we are going to achieve no matter what it costs, the world just doesn't work like that. You have to keep costs in mind through all these cleanups, and I think that we can do that and still achieve the goals. These laws, I think, have served me well, and if we can make as much progress in the next 25 years that we have in the last 25 years, I think that this river will be a grand resource for all of future generations. Thank you very much.